right, good afternoon. I'm Larry Crosby, so welcome. You've been to session 1. We talked about power fundamentals and customer awareness. Session 2 was introducing the different types of converters and integration levels. And we talked in a little more depth about LDOs and switchers. And session 3 is about how we get started and the tools that are available to help you. I've titled this session as ADI Toolbox. Okay, our agenda this afternoon, we're going to talk about how to choose parts for a power design. We're going to look at the tools that are available for selecting a part. We're going to talk about the different components that go along with a power design. So, for choosing parts, just a reminder, priorities. You know, which of these parameters are most important: size, efficiency, noise, transient response, because those priorities will give you the direction you need to choose an appropriate part to design the power rail. So let's take an example. Here is the list of power rails that we talked about in the last session. And let's just focus on one particular rail and go through the process of how we would go about choosing a part and designing this power supply. So I'm going to choose the CPU I/O rail. That's a 12 volt in to 1.8 volt out, and the max current is 5 amps. We want this optimized for size, like a small solution if possible. So here's a summary of the requirements. Note that I have the input range included because that's important. This is going to be 12 volts plus or minus 5%. And we need to choose an integration level because that will narrow down the list of parts that we have to choose from. So we could use a discrete implementation, a monolithic where the FETs are on chip, or a micromodule. And for this design, I think I'm going to try a monolithic part. And so how do we find a part? We have options. We can go to the ADI website. This lists all the parts with size and links to the data sheets. We can use LT PowerCAD. This has models for legacy LT parts and some links for Maxim parts. And PowerCAD has full design capabilities, meaning that you can modify a design, change component values, and it'll tell you what the performance is going to look like with the modified values. We can use EESIM. That is a tool that was developed by Maxim, and it contains models for legacy Maxim parts. It's a little less comprehensive than PowerCAD in that it doesn't have the capability of showing you the performance as you change or modify component values. EESIM can give you a design, it can give you a schematic, and there is a link to the OASIS simulator to look at the performance, but that requires a little more in-depth work, whereas PowerCAD will give you pretty much all the performance information right in the tool. Here are our choices: the ADI website, LT PowerCAD, and EESIM. So I'm going to jump in and we're going to look at each of these and see how we would operate with those various tools. So let's start with the ADI website. Here is the homepage for the Analog Devices website. In order to search for parts, we go to Products and click there. And in this window on the left, we select Power Management. That is the category for doing power design. When we click on that, this is the subpage for all the power management parts. And there's different categories there: micromodule regulators, battery management, LDOs, etc. For this rail, we're going to want to use a switching regulator. So that would be under this category. First off, we need a buck regulator. So that's this category, step-down regulators. And a monolithic part on the website is categorized as an internal power switch buck regulator. Remember, monolithic means the FETs are on chip and that's internal power switch. So I will click that, and it will take me to another page where now I can click here and get the table of all the different parts that are available. So this is the table that you will get from the website, and there are a number of categories that are displayed in the columns: the V-in range, the output current, the V-out minimum, whether it's synchronous or not. Synchronous means it doesn't have anything to do with synchronization. A synchronous regulator means that the bottom switch, in the case of a buck, the bottom switch is a MOSFET as opposed to a diode. Synchronous regulators are a little more efficient because there isn't the voltage drop associated with the diode, and so there's less power loss in the bottom switch. There are also other parameters that are available, and if you want to add columns, you can click here under Choose Parameters, and it brings up this window, and these are all the different parameters that you can add to this table. And there's all kinds of stuff here, but I'm going to add just one more. This one is called package area. So this will give us a column that shows for each device how big, what's the size of the IC, and it gives it to you in square millimeters. So we'll click OK, and now we see that it's added this package area column here. In order to narrow down the list, we need to make sure that the part we select is going to meet our requirements. The first one I usually go to is the V-in range. So I don't really care what the minimum V-in is, but the input power rail could be as high as 12.6 volts. That's the maximum V-in. So I need to make sure that we choose a part that can handle at least, let's say, 13 volts on the input. So we enter that. Then we need 5 amps of output current, so I need to make sure we select that. This table now shows all the devices that can handle a minimum of 13 volts in and at least 5 amps of output current. Another thing I like to do is now sort by output current, because there's probably not much reason to use a part that can deliver 10 or 15 amps when all we need is 5. So if I click on this column, it will sort the table by output current. And so here, as you see, are all the 5 amp regulators. If we scroll down, there's some 6 amp, 8 amp, 10 amp, etc. But it puts all the 5 amp ones at the top of the list. So we know that's going to be a pretty good match for what we need to do for this design. And over here in the package area, we can see here is the size of the different parts. And it shows you in square millimeters. These first two, they don't really show an output current range. So I'm not sure why that is, but they may not be appropriate for our design. So I'm going to start here. And I noticed that probably the smallest one that has a rating for output current is this one, the LT8640A. So I'm going to click on that, and it'll take us to the landing page for the LT8640A, and that's what we see right here. So it tells you the name of the part, a little description of what it is. Here's an example circuit of how you would hook it up, and there's a link here to the data sheet. So if you click this link, it'll download the data sheet, and you can save it onto your local hard drive so you can take a look at it. That's the process I would use to select a part using the ADI website. It's pretty straightforward. What's another option? So we did the ADI website. Now let's look at LT PowerCAD. This is the startup window that you get when you run LT PowerCAD. Remember, this is a suite of tools. So there are several tools that are under this umbrella. And if you hover over any of the icons, this little text box will show up telling you what that icon does. So this first green one, that's the power supply design tool. The blue one here is the system level design. That's LT Power Planner. So this is what we use to generate the power tree. This is a link for LT Spice. That's the general purpose simulator that we have. If you created a file yesterday or last week and saved it, you can reopen it here using the open file link. And there's some other tools down here, including EESIM and our toolbox. And the toolbox is where you would find things like the quick start guide and some other various Excel tools and that sort of thing. So let's go to LT PowerCAD. And if we click on this, we'll get a window. Let's just click on this. And it will open up the part search in LT PowerCAD. Here we would enter in information about the rail that we're trying to design, voltages and currents, and also the type of device, whether it's a module or a monolithic or a controller, etc. So let's enter in that information. The minimum VIN is 11.4 volts, nominal is 12, the maximum is 12.6. The output voltage is 1.8 volts, and we need 5 amps of output current. And then I decided we're going to try a monolithic part, so I click on that, and now this graphic shows in the blue box, that's the IC, and we see that the switches, the MOSFETs, are inside the box, so they're on the chip, on the die. And so now we click here, search for parts, and the tool will go through the database looking for parts that can meet all of these requirements that we've laid out. And it'll take a couple minutes to find that. And there are a number of other features that you can select. So if you have particular features that you need to have for this design, you can check these boxes, and the tool will include those when it goes through the database. So it's a pretty flexible search tool. And here's our list. This list here are all the parts that are in the database that match the requirements we've set up. And sure enough, right here is the LT8640A. That's right up near the top of the list. And to open the actual design tool for that part, we would click on this little icon here. It'll open up the design tool for the LT8640A. I've already got that open. This is what it looks like. It tells you the name of the device, the brief description here. And then these are all the parameters associated with the design for this part for the configuration that we've requested. All the blue boxes are data entry boxes, so you can enter in values in these boxes. Some of them are text, like the part number and the manufacturer. Other ones are numerical, so the nominal voltage, the inductance for the inductor, the DCR, that's the DC resistance of the inductor, etc. So the blue boxes are for end user to enter parameters. The yellow boxes are calculations that the tool does on the fly. So you can't change those, but as you change parameters, the tool will update all of those calculations for you. Here we have a design. The tool is telling us that the suggested inductor value is 0.75 microhenries. The inductor value is important because at a given operating frequency, the inductance determines what the ripple current is in the inductor. And remember from one of our previous sessions, we looked at the switching cycle for a buck converter. And as the switch node is toggled up and down by the internal switches, when the switch node is pulled up to VIN, the current ramps up in the inductor. And when the switch node is pulled to ground, the inductor current ramps down. So that peak to peak is the ripple current for the inductor. And this is a current mode controller. So the inductor current is the primary loop control parameter. That's how the part knows when to switch from the top switch being on to the bottom switch being on. And so that signal needs to be large enough so that the part can accurately switch at the same point on each cycle. If you use too large an inductor value, then that reduces the ripple current and that signal gets very small. And so the part will have difficulty hitting the same peak current value each cycle. And the result will be that there will be jitter in the switching waveform because of noise and other things in the system that kind of corrupt that small signal. Jitter in the system is undesirable because it gives rise to frequencies that are not associated with the switching frequency. So you get lower frequencies that may cause larger ripple voltage in the output and things like that. The rule of thumb that we use is something like 40 or 50% ripple current, and that's in this box right here. And so that's what the tool used to determine 0.75 was the sort of optimal inductor value. As it turns out, 0.75 isn't a standard value, but 0.68 is pretty close, and there are plenty of inductors available with that value. And so at 0.68 microhenries, we'll have 55% ripple current. That's pretty close, and it's certainly large enough to make sure that the controller can switch reliably cycle to cycle. There's also fields for the output caps, and there are two types of output caps that are available, ceramic and what we call bulk, which are usually polymer capacitors. And the tool lists the nominal capacitance, the ESR, the ESL, that's the effective inductance of the capacitor, and a box where you can enter the number of that type of capacitor that we're going to put in parallel. And there's also a box here just labeled C. And what this is the effective capacitance when the circuit is running with an output voltage. As it turns out, ceramic capacitors have a voltage coefficient. At 0 volts, the capacitor might look like 22 microfarads, but at 1.8 volts, where you have some bias on the ceramic cap, it loses some of its effective capacitance. And we'll talk about this a little more when we get to the component section. That's the design tool for the 8640A, and that's another way to select a part and get into a design tool where we can actually see what the operation looks like. The third way is to use EESIM, and so we'll go back to that and take a look. So EESIM, this is the landing page on the ADI website for EESIM, and you enter in the same type of information, the input voltage range, the output voltage, output current, and then click on the Find button, and the tool will look through its database and see what parts are available. So let's do that real quickly. The order of these voltages is a little different than it is in PowerCAD. So in PowerCAD, it was minimum, nominal, maximum. In this tool, it's minimum, maximum, nominal, just a quirk of how the different tool is set up. So I'll put the minimum, the maximum, and then here's our nominal, 12 volts. Our output is 1.8 volts, and we need 5 amps of current. So we click the Find button, and here the tool is showing us a table of parts that are available. That turns out there's 22 parts total that can deliver the current that we need. And it has columns just like the ADI website does. And so we can see, here's our maximum current. I'm going to choose a part that's a 5 amp part. Again, I don't necessarily want to use a 15 amp rated part for this 5 amp rail. So down here is the max 17506, which is a 5 volt step down regulator. So I'm going to click on that, click proceed, and it brings us to this page. And unfortunately, we have to re-enter some of those parameters, and that's just how this tool operates. So I'll enter them again. 11.4 volts, maximum is 12.6, nominal is 12, and our output voltage is 1.8, and the load current is 5 amps. And there are a couple of choices here for design trade-offs, so we can balance efficiency and size, or we can select a design for smallest size. So I'm going to click that one. And then the BOM priority can either be cost or performance. So let's click Create Design and see what happens. So here the tool is pulling up information from the database. And there is a design using the MAX 17506 that can deliver our requirement of 1.8 volts at 5 amps. And these are the various components that go around it. It's still a relatively small set of components. If you want to make changes to component values, you can do that. And I believe this recalculate button will allow you to see what's different when you make a component change. But if you want to look at the detailed operation of the circuit, you'd need to go into simulation, which takes you to the OASIS simulation tool that Maxim uses. And that's a little more in depth than we want to get into right here. But this is another way to get to a design. Okay, let's get back to our PowerPoint. Okay, so now we're going to look at components and talk a little bit about the components that go into a power converter. So a complete power converter includes capacitors, and those may be multi-layer ceramics or MLCCs or polymer electrolytic. Inductors, inductive switching regulators use an inductor as the energy storage element. There may be MOSFETs involved if you're doing a discrete design where you use a controller IC and everything else is separate. And all of these components affect the performance of the power converter. So we need to understand a little bit about them before we go off to do a design. So let's talk about the inductors first. The inductor is a coil of wire. It's typically in a magnetic housing. The magnetic housing enhances the effective inductance that you get. So you could use an air core inductor, but you wouldn't get much L unless you put a lot of turns into it. Using a magnetic housing increases the L value for a given number of turns. And the current causes a buildup of magnetic field in that core, the magnetic core of the inductor. Remember, V equals L di dt from our first session. And we have to talk now a little bit about core saturation. There is a limit to how much magnetic flux a particular core can handle. And if you reach that limit for a particular core, then the inductor does what's called saturating. And when this happens, the ability to build up a larger magnetic field goes away and the effective L value drops. And that could cause problems. There are several different types of cores for inductors. There are powdered iron cores, ferrite cores, and composite cores. And why do we care about the type of core? Well, this is one reason why. This graph shows what the saturation comparison looks like for powdered iron and for a ferrite inductor. We see the blue curve. The slope is quite shallow, so there isn't much change in the inductance as the DC current increases. And it only looks like a maybe plus or minus 10% change in the inductance. So the vertical is inductance, the horizontal is DC current. So that's interesting to note. The red curve is for the ferrite inductor. And the ferrite inductor has a very flat curve until you get to this knee point. And above this knee point, which for this inductor is maybe around 12.5 amps, all of a sudden the inductance drops precipitously. And down here at 15 or 17 amps, you have only 20% of the effective inductance that you started out with. So why does that matter? What happens if the core saturates? The L value will drop, and it can be precipitous depending on the type of magnetic material. As L drops, the peak current rises because remember, V equals L didt. If L goes down, the voltage is still the same, then didt must go up. So now our peak current is higher. If the current gets too high, it can damage the FETs or the IC in your design, and bad things can happen. The part could break, and don't like it when parts on the board blow up. So we need to be aware of this and take care when we choose the inductor. Here's another graphical example of what that looks like. You may remember these are the switching waveforms for a buck converter. So here's the switch node. It's high when the primary FET is on. It's low when the secondary or synchronous FET is on. And you see the inductor current ramping up and down. And in current mode control, the peak current is a critical value. That's how the controller knows it's time to switch state from the on phase to the off phase. Remember, the controller is measuring that inductor current continuously. And when we hit this point, the controller says, okay, switch the state of the FETs, and we go to the off state, and now the inductor current ramps down. If the inductor saturates, look what happens to that current. Instead of getting the expected value here, we get a much higher peak value. And that can be bad for the switches. You can get much higher current than you expect. And the part starts to lose control over the inductor current because the inductance has dropped so precipitously. So that's why it matters if the inductor saturates. So the circuit is designed assuming a known inductor value. If L drops, the circuit can lose control, and the excessive current could flow through the FET switches, causing damage or reliability problems. So the rule number one for switcher design, never let the inductor saturate. So we have to make sure that we choose an inductor with an appropriate saturation rating so that doesn't happen. We talked about some of the different types of inductors. The powdered iron ones have a soft saturation curve, but they have higher core loss. And core loss is a type of power loss in the inductor. It comes from the fact that with powdered iron, as you change from rising inductor current to falling inductor current, the dipoles in the magnetic material have to flip back and forth. And powdered iron magnetic material, there's a resistance to that flipping, and that resistance causes heat loss, and it's called core loss in the inductor. So the trade-off with powdered iron is they have a nice soft or gradual saturation curve, but you might get more heat loss because of this core loss phenomenon. Ferrite cores have very low core loss, so that's great, but they can have a very steep saturation curve. So you have to be very careful about what's the maximum peak current that my design might see under worst case conditions. You want to make sure you don't saturate the inductor. And then there are composite materials that a number of vendors make where they've sort of combined both the powdered iron material and the ferrite material, and they try to straddle those two types of materials and get you someplace in between the sort of good and bad characteristics of each of these types of magnetic materials. The bottom line is you need to read the data sheet for the inductor. If there isn't a saturation curve in the data sheet, you have no idea where the saturation value is, and you don't know what the curve looks like. So if you don't have a saturation curve, find a different inductor. That's how you design power supplies so that they will be reliable and nothing will go bad, even if there's a fault on the board. Okay, let's shift to capacitors. So output capacitors, we mentioned the MLCC or multi-layer ceramic chips. They have very low ESR or effective series resistance. They're small, but they have some limits to how much C you can get in a package with the ceramic caps. And there's also this capacitance versus voltage or voltage bias derating that you have to take into consideration. So the ESR range for multi-layer ceramics is 2 to 5 milliohms, so it's a very low value. That's good because that means that they provide very good capacitive energy storage. Polymer electrolytics are a different technology. They still have relatively low ESR, but virtually no loss of capacitance with bias. So that's a good thing. And there's much larger capacitance values available. So there are polymer caps that are 1,000 microfarads. They're larger than the ceramic caps, but if your design needs a lot of capacitance on the output, you may want to have a mix of the ceramic and the polymer cap so that you get enough capacitance in a reasonable size. And the ESR range for the polymer electrolytics is between maybe 6 and 30 milliohms. So still quite low, but not quite as low as the multi-layer ceramics. The higher ESR of the polymer caps can also help boost the phase in the loop response due to an ESR 0 that's formed by the ESR and the C of the polymer cap. And this can be beneficial when we look at loop stability. And you can see that in some of the design tools. So that's useful to know. If you're having trouble getting enough phase margin, maybe use a polymer cap and that might improve. A little more detail about the ceramic caps. Here's a plot. This is from one of the cap vendors, and it shows a whole bunch of, these are all 4.7 microfarad ceramic caps. They're in different package sizes, so from 0603 all the way up to 1812, a couple of different dielectrics, and different voltage ratings. And the curves show how much capacitance you'll get at these different voltage levels. And note that the caps down in this range, they start off at 4.7 microfarads with no bias. But when you get up to 5 or 10 volts, you may have less than 20% of the original capacitance. And that's going to be a problem because now you think you're buying a 4.7 microfarad capacitor, but let's say you're designing a 3.3 volt power supply. If you pick this part, you're going to get less than half the expected capacitance value when you put it on the board and actually run it at 3.3 volts. So this is something to be aware of. The higher quality cap vendors will provide these curves so you can actually see what that looks like. And LT PowerCAD includes a library of caps. And so you can actually go in and choose a cap by part number, and PowerCAD has the information about this capacitance loss with voltage and will tell you what the effective capacitance is for that particular capacitor at the output voltage that you've specified. This is a really important aspect of ceramic caps that you need to be aware of. Also note that the larger packages have a much shallower curve. A bigger package doesn't lose as much capacitance with voltage. So, you know, here, this is the 0603 part, and the 0805 is a little better, but out here, the 1206 or 1210, much, much better. So you can bias this cap up to 15 volts, and you still have a lot of the effective capacitance remaining. There's a trade-off there, size versus how much effective C you'll get. Now, if the power supply you're designing is a 1 volt rail, then you're all going to be operating up here, and it makes much less difference as to which cap case size you choose. But at the higher voltages, it's a big issue. I'm going to talk briefly about MOSFETs, and this applies only to discrete designs. So these are designs where you have a controller and separate FETs and inductor. And there are two FETs in most switching converters. There's a control FET, and in a buck converter, that's the top FET. The control FET, the circuit will have to drive the FET to pull the switch node up from ground up to V in a buck converter. And when you do that, the VDS of the FET is changing as you're driving the gate. And as a result, you have to provide a fair amount of charge to the gate capacitance in order to make that FET pull up and actively drive the switch node. The control FET has to be selected for a low gate charge, or the parameter is called QG. This is something you'll see in the data sheet for the FETs. And so you need to select a part that has a relatively low QG value. Otherwise, it will slow down the turn on of the FET, so you could get higher power dissipation. Some other bad things could happen. If it slows it down too much, then the two FETs may overlap and you get shoot through. So a lot of bad things can happen. Just remember, for the control FET, you need relatively low QG in the specs for the FET that you choose. For the synchronous FET, this is the bottom FET in the buck converter. The synchronous FET doesn't get turned on until the switch node has already fallen to ground. So there's almost no voltage across the FET. And so when you turn on the sync FET, VDS hardly changes at all. And as a result, QG doesn't really matter for the sync FET. As a result, you can select a different FET for the sync FET, and you select it for low RDS on. When people design FETs, QG and RDS on are kind of inversely proportional. If you want a FET with very low RDS on, that means the part is physically large. It has a lot of area to get that RDS on down. And as a result, there's more capacitance on the gate, and therefore the QG value is bigger. So this low QG FET that you have to pick for the control FET position isn't going to have as low an RDS on value as the sync FET, but that's a trade-off you have to make because you can't use a part with too high a QG value. A note that in a boost converter, the two positions are opposite. So the control FET in a boost converter is the bottom FET. And that's because in a boost, the switch node moves on its own when you turn off the bottom FET. The switch node flies up on its own because of the inductive action. But the bottom FET is the one that you have to drive to pull that switch node down at the start of the cycle. So the control FET in a boost is the bottom FET, and the sync FET is the top one. LT PowerCAD will show you appropriate choices for the FETs in each of those positions. So that's another benefit to using that tool, because it'll tell you, here's the best FET that we have in our library for this position. Okay, so that's all I have for today.